Welcome back, Physics Theory. This is the MP1.3 length contraction part of our modern physics MP1 section. So we looked at relativistic time. Now we're going to look at something referred to as relativistic length. And we'll see there's a lot of relativistic something or others. But in this part, we're only going to look at time and length for our MP1 investigations. So solve word problems involving length contraction, describe how to use the length contraction equation. So just like time dilation, there'll be a length dilation as well. Time intervals are not the only thing different in different frames. Space travel, lengths and distances are often different as well. According to the special theory of relativity, we can illustrate this through the following. So if we take a look at this, we could take a look at someone standing here and witnessing this movement here. Okay, and that's what we did with the time dilation. So time going by on Earth and time going by on the ship. Now we could also look at, well, what if we're looking at this and looking at either this moving or this moving? So there's two different scenarios here. So we could say this is at rest and this is moving and apply an equation for that. Well, we could as easily say, what if this is at rest and if this is moving? So if we're looking at the parts of just that part and not involving this ship decelerating or accelerating. Think of it as being at rest, then of course this is moving and this is moving. Now the interesting thing here, at rest we see that the ship is this length, but to a person seeing that ship move really, really, really fast, we can see that it contracts. It contracts in the direction of motion. Similarly, if this spaceship is at rest, look at how Neptune, the moving Neptune, compares to the Neptune at rest. Again, it contracts in the direction of motion. Or Earth, it contracts in the direction of motion as well. So if an observer sees something else moving, whether that person is at rest and seeing something move, or whether that person perceives him or herself to be at rest and something else is moving towards it due to really this motion, there's a contraction in that direction. So observers at rest on Earth watch a spacecraft traveling at a certain speed from Earth to Neptune. Notice that the spacecraft looks shorter in the direction of motion than it would be if it was not moving at all. Observers on the spacecraft, however, believe that they are at rest, and they see the Earth and Neptune move away, and notice that those planets look contracted in the direction of motion as well. So we can analyze both situations equally by using this. So notice with the time dilation, the factor of gamma, or the square root of 1 minus v squared over c squared, is divided by, whereas this one, it's multiplied. And we could go through the derivation, but we're not going to. It takes quite a bit of work there. So L, now this will be the length of the moving object as measured by an outside observer. So this will always be smaller than L, then L naught or L0. And L naught represents the proper length. So what it would be, the length of a moving object as measured by an observer moving with the object. Or we could say that this is the at rest length. So sometimes it's referred to as proper length. So the length that something should be. If it wasn't moving, how long would it be? Okay? And of course, v is the speed of the moving object as measured by an outside observer. And then c, of course, is the speed of light. Now this is a result of special relativity and applies to lengths of objects as well as distance between. So the length of objects, so the object length contracts. So to someone on Earth, they see the spaceship contracting. But we could easily say, well, someone on the spaceship, the length of this contracts, but you know what? Also the distance is a length as well, and it contracts, which brings some interesting results. So if objects contract that are moving away from us or towards us, then the distance between the two contracts as well. So objects and also distances. So the length of an object moving relative to an observer is measured to be shorter than along its direction when it was at rest. And we could also talk about that where it talks about the length of an object we could also replace that with the distance between two objects. So length or distance between objects are measured to be shorter. So if you want to get to somewhere quicker, or drive really, really fast, so not only are you speeding towards there, but the length contracts as well, which is crazy. So this is called length contraction. The length L naught is called the proper length. It is the length of the object when the 2 points, or distance between 2 points whose positions are measured at the same time, or when we're at rest. When we're at rest, as determined by observers at rest with respect to the object. So the equation gives the length that it would be measured, and then the equation gives the length that will be measured by observers when the object moves past them at speed v. So that is L. That is the L. So that will be the contracted length, or the smaller length. It's important to note that length contraction occurs only along the direction of movement. So for example, the moving spaceship is shortened in length, but its height is the same. So, and that's kind of weird, right? So it'd look like we would get skinnier. Length contraction, like time dilation, is not noticeable in everyday life because, yeah, that V is usually very small, which means this is going to be very close to 0, and 1 minus 0 is 1, and of course that factor of 1 doesn't change anything. But if we're talking about big speeds, it would change. All right, so let's take a look at an example here. Painting contraction. A regular painting measures 1 meter tall and 1 meter wide as seen over here, okay? It's hung on the side of a spaceship which is moving past Earth at a speed of 0.9 c, which would be 90% the speed of light. So here we have someone on Earth, and then here we have someone on the spaceship. There they are, and here's the painting. And of course that spaceship is moving by, right? What are the dimensions of the picture according to the captain on the ship? Well, according to the captain on the ship, this painting isn't moving with respect to him. So A, nothing. What are the dimensions of the picture? So nothing out of the ordinary. There is no change to the painting. Okay, it's still 1 meter high by 1.5. But to someone seen by Earth and seeing this painting move, painting is moving with the ship. So we have to apply this formula now. We have to apply this relationship. L is equal to L naught multiplied by 1 minus v squared over c squared. All right, so now L naught would be the length of this thing if things weren't moving. Now we only have to worry about, length in direction of movement. So if I assume this painting is hung normally, it's this distance that's going to be affected. So that's the one I include here. So if things weren't moving, the length of that painting is 1.5. But of course we are moving at 0.9 c, which is going to be all squared over c squared. Okay, so as you can see, we're going to get 1.5, 1 minus, so 0.9 squared is 0.81. C squared over c squared, so cancels out. So we'll get 1.5 over 0.81. So we get 1.5. And let's see, what does this work out to be? Point multiplied by the square root of 1 minus 0.81, which would be 0.19. I believe that's right, 10, 9, 10. And then when we multiply that out, we get 0.65. Look at that. So, yeah, so let's just check that out on the old calculator here. So the square root of 0.19 equals that. And then multiplied by 1.5, 0.65. So look at that. So therefore, the painting, there we go, I just put that into here so I have that picture. So it's still 1 meter tall, but in the direction of movement, it shrunk. It got skinny. 0.65 meters. So isn't that interesting? To someone on the ship, it looks the same, but to someone who's watching it move, it has shrunk. All right, we'll leave it there. We'll come back for part 2 here in a second.